Okay, this is Math 105, section 2.7. We're going to talk about inverse of a function. Okay, so that's a rule that acts on the output of a function and produces the corresponding input. In other words, it goes backwards. So the inverse undoes or reverses what the function has done. Okay, not all functions have inverses. So if they do, we call them one-to-one. Okay, so think of like, if we have a set of inputs that go to a set of outputs, well, we just reverse them to get the inverse function. So in order for a function to have an inverse, it must be a one-to-one function. So let's explain what that is. Okay, so let's look at a function, first of all, that is one-to-one. Now that means each input has exactly one output, and each output is unique. In other words, there's no shared outputs. Each output is different. Okay, so we don't have repeated y's. Okay, so 4 goes to 10 in this case for f, 3 goes to 7, 2 goes to 4, and 1 goes to 2. There's no repeated x's, which makes it a function, but there's also no repeated y's, so we say f is one-to-one. Okay, g is one that's not one-to-one. So f does have an inverse, but g does not. The reason is because now it is a function because we don't have a repeated x, but we do have a repeated y. 4 goes to 10, but 3 goes to 4, and also 2 goes to 4. So we see that we have that repeated output. And then 1 goes to 2. So this is not a one-to-one function. So this function g does not have an inverse. So we note that f never takes on the same value twice, the y, okay? Where g does take on the same y value twice, same value. The value of g is the function y, and the value of f is y, okay? Both 2 and 3 for x have the same y for g. Okay, so g of 2 equals g of 3. So there, see, we have a repeated y there. But for x, there's no repeated y. So f of x1 is not equal to f of x2 whenever we have two different x's. Okay, so we call this property one-to-one, and that just means that whenever you have two different x's, you're going to have two different y's. Okay, so there's basically no repeated y. Okay, and this is just a formal definition. A function with domain A is called a one-to-one function if no two elements of A, the domain, have the same image. That is, whenever we have two x's in the domain that are different, the y's will be different also. Okay, so we can say if f of x1 is equal to x2, then x1 is equal to x2. In other words, if we have the same y's, it comes from the same x. But this is kind of a little more direct way of saying that. Whenever you have two different x's, the y's are different. That's what we define, how we define one-to-one, and that determines whether a function has an inverse. So we can see repeated y's graphically. We're going to see that a horizontal line will intersect that graph more than once. Okay, and you can see a repeated y, that this x1 gives us the same y as this x2 does. Okay, so there's our repeated y. So we use a horizontal line to test for one-to-one. If we have a repeated y, we're going to cross that graph more than once with a horizontal line. So we can see that f is not one-to-one here. Okay, and that's called our horizontal line test. So remember, we use vertical line test to test for a function. We use horizontal line test to test for one-to-one. Okay, so a function is one-to-one if and only if no horizontal line intersects its graph more than once. Okay, so if you've got a horizontal line that intersects your graph more than once, let's do another one. Okay, something like that. Let's do a different line going through. You can see that this function, whatever it is not one-to-one because it crosses that function more than once with the horizontal line. So that function does not have an inverse. Okay, let's look at an example with f of x equals x cubed. Is that one-to-one? If x1 is not equal to x2, then x1 cubed should not equal to x2 cubed. In other words, two different numbers cannot have the same cube. Okay, we can see the graph of that and look at horizontal lines going across, and we're not going to cross that more than once. Now you might think it does it at the x-axis, but no, it doesn't. It only crosses it at one point. So yes, this is a one-to-one function, passes the horizontal line test, so it does have an inverse. It is a one-to-one function and it has an inverse. Okay, so we notice that that function x cubed is always increasing, and it's also one-to-one. In fact, we can show that every increasing function is one-to-one and every decreasing function is one-to-one. But let's explain what that means. When you talk about an increasing function, that means it's always going up. that y is always going up as we go along with x. Okay, and we can see the blue lines or horizontal lines going through that function will not cross it more than once. It's 1 to 1. And the same with the decreasing function. This is a function that keeps going down. Okay, it never goes. That's actually still going down. It's really not a horizontal line there. Keeps just decreasing all the time. And we can see with drawing those blue horizontal lines through, we can only cross that function once. We can't cross it more than once. So an increasing function is always 1 to 1, which means it has an inverse. A decreasing function is always 1 to 1, which means it has an inverse. Okay, so let's talk about the definition of the inverse of a function. Okay, f has to be 1 to 1. Okay, has domain A and range B. Okay, then the inverse function uses this notation, that f negative 1. It looks like f to the minus 1 power, but it's not. And that has domain B and range A. Okay, so we can say f inverse of y equals x. See, we're putting y as our input and x is our output. Okay, remember we have y equals f of x, where x is our input and y is our output. Well, now you're reversing those. Okay, so what you're doing is you're switching your x and y when you have your inverse function, and that's what we'll be doing algebraically, is that we'll be switching x and y. So a way we can talk about this is that, you know, our function f goes from x to f of x. It goes from this from this A domain to this B range. Our inverse function does the opposite. It goes from the range to the domain. It goes from B to A. Okay, so the domain of my function, original function, is the range of the inverse, and the range of my original function is the domain of the inverse. So the roles get switched. Okay, so domain of A is range of B, okay, and range of B is domain of A. Okay, and then domain of B is range. Sorry, let me restate that. Domain of f is A, and range of f inverse is A. Okay, and then domain of f inverse is B, and range of f inverse is A. See, they get switched. Okay, let's look at an example with some specific points of the function. So if f of 1 equals 5, remember x is our 1 and y is 5, then f inverse of 5 is 1. So we're switching them, okay? Because f of 1 equals 5, we switch them. Okay? If f of 3 equals 7, then f inverse of 7 is 3, okay? Because f of 3 equals 7, okay? And finally, if f of 8 equals 10, then f inverse of is minus 10, sorry. Then f inverse of minus 10 is 8, because f of 8 equals 10. So what we're doing is we're switching the x and y. You know, we're going, this takes us from 1 to 5, the inverse takes us from 5 to 1. This takes us from 3 to 7, the inverse takes us from 7 to 3. This takes us from 8 to minus 10, and the inverse takes us from minus 10 back to 8. Okay, so this is kind of showing a mapping where the function is going forward from 1 to 5, 3 to 7, or from 8 to minus 10. You know, where A is our inputs, our domain, B is our outputs, our range. And then f does the opposite. F goes from 5 to 1, and 7 to 3, and minus 10 to 8. And our domain for f inverse is B, 5, 7, minus 10. And our range is A, is 1, 3, 8. Okay. Be careful of the minus 1. That's not an exponent. So f inverse of x, f minus 1 of x is not 1 over f of x. Okay. It's not a reciprocal. It's not a multiplicative inverse. It's the inverse of the function. So this is not to the minus 1 power. Okay. If we had to write that, we would have put parentheses around. But let's not worry about that. But just understand that this notation does not mean 1 over f of x. It means the inverse function. Okay. Okay. So we say by definition, the inverse function f minus 1 undoes what f does. Okay. If we start with x and then apply the function, then apply f inverse, we arrive back at x, where we started. Okay, and then similarly, f also undoes what f inverse does, so it works backwards too. Okay, so we can say the definition of inverse of a function is this. Okay, so f is a one-to-one function with domain A and range B. Then its inverse function, f minus 1, has domain B and range A, and we define it this way. F inverse of y equals x is the inverse, and then f of x equals y is the regular function for any y and b. Okay, so we say that f and f minus 1 are inverses of each other because one is inverse of the other and vice versa. Okay, so let's now figure out how we're going to find the inverse. You know, we're saying y equals f of x and we want to get to f inverse of y equals x. Okay. So what we can do is, now we can do it two different ways, but the book says to do this. Solve the equation, start with y equals f of x, and solve the equation for x in terms of y. In other words, get x by itself, okay? And then we interchange x and y, okay? And that gives us the equation, y equals f inverse of x. Okay, so the first step is to solve for x in your equation. So get x by itself, okay? And then switch x and y, okay? Now the other way to do that is to switch x and y first and then solve for y. Okay, so we can do that as well. And we'll kind of look at both methods in class. Okay, so these are the steps. Write your equation down, y equals f of x, whatever it is. Solve for x, okay? Get x by itself. Switch x and y, and then the result is your function. Okay. Now we can switch steps 2 and 3. Okay. In other words, we can solve for y, or sorry, yeah, we can solve for y. Sorry, we can interchange x and y first, okay, and then solve for y in terms of x. Okay. That's what I was saying from the earlier slide. Okay, so let's look at an example. Let's say our equation is f of x equals 3x minus 2. Remember, that's the same as y equals 3x minus 2. Okay. First we'll solve for x, so we're going to get x by itself. So we're going to add 2 to both sides, then divide both sides by 3, and we have x equals y plus 2 over 3. So we've taken our original function and just solved for x, got x by itself. And then the next step is just to switch x and y. So this was x before and this is y, so we switch them. So now we just have y equals x plus 2 over 3, and that is our inverse function. So f inverse of x, f minus 1 of x, is x plus 2 over 3. Okay, a rational function, remember a rational number was a ratio of integers, right? Is a function defined by a rational expression. So it has a rational expression in it. In other words, an expression divided by an expression. Okay, so we'll find an inverse of a rational function next. Okay, so let's say this is our rational function. Y, or f of x, equals 2x plus 3 over x minus 1. Okay. So first we write it as y equals that, and then we're going to solve for x first. So first thing we do is, now it might seem like we can't really solve for x, but we can in this case. But first thing we do is want to get rid of the denominator. So we're going to multiply both sides by x minus 1, so that's what we do there. Okay. And then we distribute here. So y times x and y times minus 1. So yx minus y equals 2x plus 3. Okay. Now, to get x by itself, you want to take every term with an x in it and put it on one side, and every term without an x on the other side. And then we'll be able to factor out the x. So that'll be our next step in the next slide. So we move things around so we've got all of the x terms on one side. In other words, so anything with an x in it goes on one side, and anything without an x goes on the other side. So the non-x terms go over here, and the x terms go over here. Don't worry about the y there. Okay. So now we're going to factor out the x on this side. And when we do that, we have x times y minus 2 equals y plus 3. And then we can just divide both sides by y minus 2 to get x by itself. You see that? If we do that, we get x equals y plus 3 over y minus 2. Okay. And then our inverse function, we just switch x and y. So this becomes an x, this becomes an x, that becomes a y, and then we have f inverse of x equals x plus 3 over x minus 2. Now what we can do is find the domain of this function, and the domain of this function is going to be x is not equal to 2, right? So we can go back to our original function, which was this. Okay, we found the inverse of the original function, right? And then we can say, well, because the domain of the inverse function is x is not equal to 2, then the range of the original function over here will be y is not equal to 2. And the reason for that is because we switched x and y to get from this function to this function, right? So if we're talking about x here as a domain, we're talking about y here as the range. So we can find the range of a function by finding its inverse and finding the domain of that inverse function. Okay, and also similarly, we can say, okay, if the domain of this function is x is not equal to 1, then the range over here in the inverse function will be y is not equal to 1. So do you see how those connect? That the domain of the function is the range of the inverse. we just switch x and y. So x is not equal to 1 becomes y is not equal to 1. And then the range of the original function is the domain of the inverse. Y is not equal to 2 becomes x is not equal to 2. So that's basically how we find the range of a function without knowing its graph, is we take the inverse function and find its domain. So we found the domain of the inverse is x is not equal to 2, which means the range of the function that we originally started with is y is not equal to 2. Okay, we're graphing the inverse of a function. Okay, if a and b is on the graph of f, then b of a is on the graph of f inverse, and that's true for any 2 points, any point that is on the graph of f. So any a-b pair that's on f will be a b-a pair on f inverse. Okay. So what does that mean? Well, if ab is here, then BA is over here. Okay? And what we're doing is we're reflecting that point across that line y equals x, and y equals x is the one that cuts through the origin and cuts halfway through the first quadrant and the third quadrant, right? So AB goes the same distance across that line on the other side to get BA. Okay? So we can say if we have a graph of a function f, then the f inverse is just going to be a reflection of that graph across the line y equals x. That's symmetry, but it's symmetry across a slanted line, right? So we just reflect that graph of the blue one, f, to get f inverse, the red one, across the line y equals x. And that's true for any function in its inverse. So we can say this: the graph of f inverse is obtained by reflecting the graph of f in the line y equals x, or across the line y equals x. Okay, so let's look at a couple examples. Sketch the graph of f of x equals square root of x minus 2. Remember, we start by plotting y equals square root of x and moving it to the right by 2 units. Okay, so here's our graph of square root of x minus 2, arrow going that way, right? And then if we want to graph its inverse, now it does have an inverse, it passes the horizontal line test, we just reflect across the line y equals x, right? And we do that, we get this graph, which is actually y equals x squared plus 2 for x greater than or equal to 0. So let me draw the domain and range of this function so we can see it. Here the domain is, what is it? X is greater than or equal to 2, right? And then the range is y is greater than or equal to 0. Well, for the inverse function, what's our domain? Our domain is, now we're taking the range here, right, and changing y to x. So the domain would be x is greater than or equal to 0. And then we can take the range from this, we can take the domain from this and make it the range here. So x is greater than or equal to 2 becomes y is greater than or equal to 2 over here. So that would be our range. Okay. And we can kind of see that, you know, as we look at the graph, y is greater than or equal to 2, x is greater than or equal to 0, right? And then we can see how they switch, right? That this becomes, well, let me draw little lines between these just so you can see that. I'll use a blue line there. So domain of the f is the range of f inverse, and the range of f is the domain of f inverse. Okay. And we switch the variables. Okay, and here's how we find the inverse. We set up with y equals square root of x minus 2. Okay. And we want to solve for x. So we're going to square both sides, right, to get rid of that square root. So we get x minus 2 equals y squared. Add 2 to both sides, and we get x equals y squared plus 2. So there's our function solved for x. Our next step is to switch x and y. Okay, so we switch x and y. So we have y equals x squared plus 2, which we define as f inverse equals x squared plus 2. But we have to specify that x is greater than or equal to 0. We can't use negative x here, right? Because then we don't have a one-to-one function if we use the whole parabola. So we have to make sure that we specify that the domain is x is greater than or equal to 0 only. It's not all reals. Okay. Okay? We'll look at some examples in class and do some other, look at some basic functions and then some other more, complicated algebraic functions and look at the inverse. And we'll look at the other method too, where we're switching first and then solving for y to get the inverse. Okay. But either method is acceptable.